This
So,
conference will now be.
so, welcome everyone for the last call in 2022. It will be like the 60-second call, and today we have Fred Steinhauser, which is going to talk to us about basically the application for precision time in power systems. So, like precision timing for digital substations. Like always, I'd like to introduce the speaker. So, Fred Steinhauser, studied electrical engineering at the University of Vienna University of Technology, TU Wien. That's where I studied my first PhD, and my dad as well. So it's very close to me, where he obtained his diploma in 1986 and received a Doctor of Technical Science in 1991. In 1998, he joined OMICRON, where he worked on several aspects of testing power system protections. Since 2000, he worked as a product manager with a focus on power utility communication. Since 2014, he is entirely dedicated to the power utility communication business of Omicron, serving as an IEC 61860 expert and digital substation evangelist. Fred Steinhauser is a member of TC57WG10 of the IEC and contributes to the standards in IEC 61850. He is one of the main authors of the UCA implementation guidelines for sampled value 9-2LE. Within IEC TC 95, he contributes to IEC 61850 related topics. As a member of CIGRE, he is active with the scope of SCD2 and CSB5. He also contributes to the synchrophaser standard in IEEE C37.118. So there are a lot of a lot of numbers here and codes and everything. I mean, it's different nomenclature. It would be great. Maybe we can touch on some of that. So, with no further ado, Fred, the floor is yours.
Thank you, Ahmad. Yeah, you already quoted some of those terms which are well known for the power utility guys, but not so much in the rest of the world. So I probably can now skip this who am I slide and right go into the question, yeah, and what has this to do with precision timing? And it's actually Omicron who is involved in this precision timing with his products. And this started with the products for protection testing. This is where Omicron grew up with, and this is still making up the biggest part of our business. There we had a use case called end-to-end testing, which is a distributed time synchronized testing application where you do a time synchronized injection and recording at two ends of a power line. And as soon as GPS receivers became available, already back in 1993, we had the first papers about this, how we do that. And then we got into this field of power utility communication. This started already in the early 2000s and yeah, developed itself as a real uh, business entity inside Omicron about 10 years ago. And there are also such distributed time synchronized testing cases, for instance, to measure timings, propagation delays, and so on. And of course, in IEC 61850, there are now new applications which heavily depend on time synchronization. And this is how we really got involved in that. And this was something that is really really interesting me, where I always was working for. And I think this time synchronization topic is a precondition for the digital substations of the future. It will not happen without it. One observation we made when we implemented tools in this regard for the electrical power engineers, we looked around about the other products which are around. For instance, for the telecom engineers, we had to come to a different level of usability. So the power engineers are not geeks in this field of timing. So they need to do it differently. They need different tools, and this is something that I think we also have achieved. But now, stopping with this background, let's go into the applications that we see for precision timing in the electrical power industry. And of course, this has been very much pushed since we have these GNSS systems around. As I said, as soon as GPS receivers came up, we already made use of it. And one application that already worked and still works, even without, let's say, external time synchronization, is differential protection, where the involved relays sometimes synchronize themselves. There is actually a black fiber between the two relays, and they do some ping pong, which is very similar to what PTP actually does. But it's a totally, let's say, proprietary thing, and you even cannot mix products from different manufacturers. And yeah, it's a kludge from my point of view. Then fault location, of course. Also, for a very long time, there are products which measure the times when faults are seen at different points in the network, and doing calculations for the fault location from that. Yeah, the speed of light on the line is the most important factor for that. So you can estimate that these people were also very soon after the microsecond or something better. Then there is this topic of the synchrophasors, which are the measured phasors of the power system quantities, again in different points on the network, and to put them in a sound relation with each other, they need to be measured time synchronized so that the phase relationships between those measurements really make sense. I already talked about this end-to-end testing. It's still a topic, and it's remaining a topic because it's the final truth to find out if your protection system really works. And last but not least, there is the topic of fault analysis. When you want to find out what really happened, you have to pull out the fault recordings of the devices and then look into it. And this is done really well if you have it time synchronized. But to come up with a counterexample in this regard, I want to go back to this blackout, which happened in August 2003. And as it happens, I was exactly over there in the States on this day. The days before August 14, I had been up in Michigan. I would have been in this area, which is in this red ellipse and black. But on that day, we had a meeting with a utility in Ohio, and we had arranged dinner with them. But they came in very late, and they said they had a problem. They had to make sure that they still have the lights on. And they told us that north and northeast of us, everything had gone black. This case was then investigated. The final report of these investigations is shown here, the title page. Everybody can find this and download it if it's of interest. It's not explicitly written in this report, but I have been told that a big part of the work was to align the recordings. And there was almost no usable timestamping at that time. So we had, in 2003, we had GPS available for 10 years already, but there was no big effort made to make the fault recorders appropriately time-stamped. The power engineers have methods to take these fault recordings and identify some characteristic events in the curves, and all the related tools for looking into these records have features to time shift this stuff and to align it. So that was much of the work, and many people are still happy with that, although you delete some kind of information if you align it this way and don't have it timestamped correctly, because all the propagation times in between in an extended system are effectively deleted by that. And out of this report, there were some proposed measures. You see, in this snippet, I have only shown a small part of these proposed measures. And one of this is number 28, require use of time synchronized data recorders. Surprise, surprise. So this underlines, I think, that there is really a need, not only in this regard, in the electrical power industry. Now, where are we and where are our applications in the electrical power industry? And I aligned that a little bit on that, what I would call the uncertainty scale. With IEC 61850, in particular with the sampled values, we were pulled into this 1 microsecond ballpark, I would say. And this is very well covered with PTP. So this protocol serves us very well to achieve this. And it's good and mostly good enough, of course. I talked about the speed of light, and great figure in imperial units is 1 foot per nanosecond. The fault location guys would like to go a little bit below 1 microsecond to increase the accuracy, but also PTP can deliver that. That's no problem. If we get the clock and also with GNSS, I think we can go down into 200 nanoseconds uncertainty, and that should be also good for that. So here we are around the 1 microsecond ballpark when we talk about precision timing. Of course, we have more relaxed use cases. So how did we get to these figures? And first we can take a step back and look what's our reference. Our reference where we are really moving ourselves on the time scale is the power system frequency, or the quantities in the power system, which have cycle times of 20 milliseconds or 17 milliseconds roughly. And here you see some of the characteristic figures. In the end, we get 1 electrical degree in the power system with about 50 microseconds time uncertainty, and so on. So 5 microseconds is 0.1 degree, and that's already something. There are not too many devices which can really measure phase angle to 0.1 degree uncertainty. That's really already a challenge. So here we are coming from. But let's see where we are going to. This is a figure out of this implementation guideline for sampled values. This is now more than 15 years old. I think it was released before 2005. And here is how we have drawn the window, the allowed sampling inaccuracy for merging units. And what we had at that time was not yet PTP. We talked about the PPS distributed via an optical fiber. And what you see here is even 400 meters of optical fiber between merging unit 1 and merging unit 2, which accounts for 2 microseconds of timing difference. And so we came to this plus minus 4 microsecond figure. So we can go very well with that, what PTP delivers. And this was, especially for this application, very, very soon adopted to assure this timing that we have for sampled values. Another case are the already mentioned phasor measurement units, or PMUs. And the characteristic figure is the so-called total vector error, which is made up by the timing error plus the magnitude measurement error. And of course, if you have a total vector error limit of 1% and have exploited that already with the magnitude error, you're not allowed to have any timing error. And vice versa. If your timing error takes up everything, you cannot allow a magnitude error. But here in this blue, yellow, and red circles, which represent total vector errors of 1.5 or 1/4%, there is the area where the combined magnitude and timing error still satisfies this total vector error condition. And you can see the standard still asks for 1%, but if you wanted to go for 0.5%, you would be able to achieve that with the timing errors between 5 and 10 microseconds. So everything which is good enough for sampled values of merging units is also good enough for PMUs to achieve a reasonable accuracy for our power system applications. To standardize this even further, the electrical power community has produced its own PTP profiles. One of them is IEC 61850-9-3. We call it the power utility profile. And the goal of this profile is to stay close to the standard profile. It should be possible to utilize a standard clock to tune the parameters and make it then working as specified in this profile. It's also called the basic profile. And the IEEE profile, the old power profile, which came first, is now seen as the advanced profile. But the use cases are well served with the basic profile, as we call it, 9-3. These profiles have some properties in common. They all work on layer 2. We use the peer-to-peer mechanism, and it's working fine when we overcame all the teething problems of this. But since it's PTP, it's pretty well working. There is also a consideration in these profiles how we can maintain the accuracy along a chain of a certain number of switches where we distribute the time along. We talk about 16 hops, and you see here the figures that one hop should only contribute 50 nanoseconds. and the master clock should not contribute more than 200 nanoseconds for the error. So things like that are already written down and thought through. And this is how the power system engineers see that. And actually, this is a very pessimistic view on the whole thing. So I sat down and calculated that a little bit. And I assumed that the uncertainties are uniformly distributed errors in these bands, plus minus 200 nanoseconds or plus minus 50 nanoseconds. And then you come to some standard deviations. And when you count this up for 16 hops, you come to a standard deviation for the whole chain, which is about 160 nanoseconds. And I also did a simulation on that verified that very nicely. And actually, what we can expect in practice is much better than this 1 microsecond figure. And something like that was also confirmed at measurements on the interoperability meeting in 2017. Of course, not with 16 hops. We didn't have so much equipment with us, but within those few hops, we could verify that these statistics for the proliferation of errors really works. Good. So much for the hardcore technical part. And now it gets a little bit different. It's getting very social now, or psychological now, because I think there are technical solutions around, but it is a challenge of its own to tell this to the people and make them believe. And to go back a little bit, I want to make you aware that electrical power engineering is a field of expertise with a tradition. I first had here a much nicer picture of a control room somewhere in London, but I don't own the rights at this picture, so I didn't dare to use it here. But I found some other pictures I have taken in a power station in Canada. And this power station delivered energy for the first time in 1922. That's exactly 100 years ago. And you see here that there is almost patina. It's nicely cleaned, but you see here somehow this prestige and the tradition which is behind at least this building. And on this generator, this is no longer the one from 1922, but somewhere on one of these little tags there is a patent from 1933 quoted. So there has been done a lot. And it's working well. Yeah, at least I have not seen a lot of power outages. So this is a very good system, and there were very good engineers doing very good work. But now things have changed. Much has been achieved. And we still are facing the situation that the established methods define the view on the problems. And just by chance, I ran across a YouTube video, a presentation given by Paul Watzlawick. He's an Austrian American psychologist who worked in Palo Alto and lived there for a long time. And he, for instance, has written a book, The Guide to Unhappiness. But the YouTube presentation, which is unfortunately in German only, is titled When the Solution is the Problem. And it is about our behavior to repeat proven behavior to always try to apply the same solutions, even if the environment has changed, when the conditions to choose a solution are not the same anymore. And this is a psychological factor that I begin to understand now after 20 years in this industry. So you can talk with a power systems, especially protection guy, and he will give you a long talk about what has been achieved without time synchronization. And at the same time, he might let you know that nothing more is needed because it worked well. So it's not even desired to bring too much of this precision timing into the systems because it wasn't necessary in the past. In the end, I must say the electrical power industry has not yet embraced precision timing. There are a couple of people working on advanced topic, knowing that they need it, but the industry as a whole is still not really fully into this topic. And this is one of my challenges to change this a little bit. Just in March, I attended a webinar and made a quick screenshot when this poll result here was shown. And from the title, you can see it is something which is addressing new technologies. And at least I expected that the audience is made up of those people who are called open minds or tech-affine people who at least are somehow familiar with the time sync topic as well. But even here, only less than half of the people regarded precision time as a future need. And this is even among a group which I would call advanced users. This is also reflected in the value that is attributed to the assets in this regard. When you look here at a circuit breaker, which can cost around $100,000 or euros or whatever you want in this ballpark, and you need 3 of them per feeder, and there are many feeders in a substation. And this is okay because it costs 100,000 euros. Yeah, that's how it is. And it's similar with these high voltage protection relays. They can cost around $10,000. And also this is accepted because this is a very important asset in the view of the power system people. And now we need other components to make this communication in the substation work. And we need very good Ethernet switches with transparent clocks, of course. And when those cost 10,000 euros, oh man, this is regarded expensive. And we see the same pattern. Even if a GPS clock would cost, let's say, 5,000 euros, this is maybe even more expensive in the view of these people looking at this with this power system background. And of course, there are apprehensions, and these are also expressed in many ways. So the worst thing is after a presentation where a guy showed something very nice and new about the protection system, and he was so careless to say that he did some timing with GPS receivers. You can bet that there is somebody coming up during the Q&A and asking, yeah, but how will this system work when the GNSS is spammed or spoofed or jammed? Yeah, these problems are always brought up, often in a way to say this whole stuff isn't usable, and you better stay away from it. That's very unlucky. Now we are faced with this attitude, which I would even call not very friendly towards time synchronization. And on the other hand, there is stuff around where these people don't have an idea of. And there is a real big communication gap between the timing world and the electrical power system world. Besides the fact that this timing thing needs to be accepted as a whole. So we have everything around and available what we would need to make a very good and reliable precision timing solution for digital substations. I have listed this up. You all know this. I don't need to tell you about that. And besides having these components available, there comes a second challenge, and making a real timing system out of that, to do the timing system integration. And the people who are doing digital substations now, especially with sampled values, they are going through this system integration of the timing system currently. And this is really something which is not their home turf. It is a complex task which needs a lot of knowledge about the components, how they work, how they are to be configured. You need to know that when you design it, and you already need to know how to test it. And this is really something where you need the related specialists. Some of the big vendors work themselves into this topic. So when delivering a substation automation system, that they can also deliver this kind of service. But I think there is even some room for other people who could really focus on that topic with a specialized expertise. So what I wish to see is an offering to the electrical power industry that is somehow similar to that what I have sketched here on this slide, without using any terms which are anyway used in the timing industry, because what we have here is an EPRTC. So the telecom guys and some others, they have something like this. And they know that this is not to have for 5,000 euros, because the atomic clock is a little bit more expensive, but it's, in my point of view, not too expensive when you compare it with the price of a circuit breaker. And when somebody would put such a system together for the electrical power industry and tell them which problems with jamming and spoofing and whatever are already taken care of, what kind of holdover we have, how we can ride through days, weeks, months of problems with GNSS. If we had something as a complete package and not just saying, here you have an antenna, here you have this, here you have that, make a timing system out of it, then we could probably convey this message a little bit better. When Googling after things like that, I already found something. It is around. This EPRTC stuff is, of course, offered, but it is described in a way that it is maybe for the telecom guys or those who are used to deal with this in more detail. So we need to find a language how to bring this over to the power system guys. Another challenge that we have are these redundant networks in the substations. And of course, we want to have redundant timing. So this, what I have sketched here, is already a redundant system. But many power system people are convinced that more will be better. So they often use clocks with two ports that they then connect to both of these networks. Then you don't have two, then you have four clocks. Then you have to set four parameters and making a very predictable and fail-safe system with a very good failover behavior becomes more and more complicated. Also here, the best practice has not yet been fully established, and there is still some more to do to make this really reasonably and well working. It's almost a little bit unfair to say this generally about the electrical power industry. There are some people like those here from Statnett in Norway who have presented at the ITSF 2022, so a little bit more than a month ago, their project. I have just stolen this slide from their presentation, put it in here without any detailed explanations, but they have really done it right. So they have these cesium clocks in place. They want to establish white rabbit links between their, let's say, timing centers. They have really elevated that on a level which has everything you could only wish of such a time distribution system. But remarkably, these findings are then presented at the timing conference, and I haven't seen it presented yet at the power system conference. Now, since we are talking about OCP TAP, let me see quickly if there is a place in the electrical power industry for the time card, for instance. And when you look at these power system devices that we typically have, these are purpose-built special boxes, environmentally hardened and everything. And of course, this is no habitat for a PCI card. So we have a very good Ethernet controllers. All of this stuff today must be able to support PTP, but no place for a time card. But there is a trend. Utilities are asking more and more if we cannot deploy our applications into virtual machines on application servers. And I have put here up some pictures of typical products which are advertised for this purpose. As boring they are to look at, the backside reveals it's a PC and it has PCI card slots. And this is definitely a place where a time card could get in. And it would also make very much sense because you could then time synchronize multiple applications running on such a server. As said, the holdover feature would be most welcome. I had to quote Heiko Gerstner, who coined this term. Holdover is our best friend, also on the ITSF 2022. And the time card could bring this feature into such an application server. I see a chance for that. And finally, because this is about open source, open source is also making its way into the electrical power industry. The Linux Foundation has set up the LF Energy Initiative, and you see here some projects which are conducted under this umbrella. Also RTE, the transmission system operator of France, which is a really powerful company, has made a commitment to open source. One company that we work with is Alliander. They even have a group which is working on such open source projects. One of them is Compass. And I will come back to that soon because we have also a connection to this. What I recently heard is, yes, with these application servers, we need a virtualization platform. There are people saying, yeah, we should do this with an open source and not with one of these known virtual machines from the big vendors for the reasons you might imagine. Closed source has some issues that many people don't want to have. Yeah, with this Compass project, we are connected through OpenSCD. This has been kicked off by former employee of OMICRON. It is an open source project now, and it is there to manipulate this IEC 61850 system configuration files. I don't want to go into this, but yeah, open source is also stepping into the electrical power industry, but also here, power engineers don't have problems with closed source and legacy solutions as long as the vendors make it work. Also here, there is some work to be done to convince the community. So let's sum up. We have applications in the electrical power industry where we really need precision timing. The digital substation will need precision timing, but it's not fully recognized yet. We have solutions, but we need to communicate that better to the people in the power community. The time card might find a place in the application servers, and open source projects are also targeting the electrical power industry. And here I'm at the end, and thank you very much for your attention.
Thank you, Fred, for this amazing, informative presentation. So let's open the floor for questions. So any question from the audience? Please don't forget unmute yourself.
Yeah, one question, Fred. This is Michelle from Meta. You referred in your deck to the use of transparent clocks in the power profile, which I'm aware of. I wanted to know if you are aware of any kind of monitoring work that has been done, or work that has been done to monitor, for instance, the behavior of transparent clocks that are used as part of that profile. Thank you.
Yes and no. I'm not aware of systems that do constantly monitor the behavior of specific transparent clocks. But sorry to mention that. It sounds a little bit like a sales pitch, but we have a product which is actually an intrusion detection system, a cybersecurity appliance. And this is not only looking at the bare packets, but also on the context. And it is also looking at PTP packets and on timestamps of the exchanged information. And if there would be something, let's say, not consistent or not logical, this device would throw an alarm. But it would not give you a statistic about the quality of the transparent clock. But there might be something around like this.
Okay, fair. Thanks for your answer. Yeah.
Any more questions?
I have a few questions. First, thank you very much for this presentation. It's fantastically on point. I've been working here from the University of New Hampshire in this power profile certification and validation space for a number of years, trying to work with the industry and certainly see the same slow acceptance of 1588 in these spaces. So we've been working with IEEE SA, NIST, and others to try to establish this certification for transparent clocks and other devices. While this is coming online based on the 61859-3 and others, our next concern area that I hear most often is resiliency, redundancy. Is HSR PRP your go-to answer, or is there a different 802.1 CB solution or some similar solution that you're looking at for defining resiliency from a profile perspective?
Oh, that's a mouthful. Yeah, maybe we have met, and at the ISPCS 2010, I was at the University of New Hampshire, and
Yes, likely.
yeah, and now to this HSR PRP stuff. I think your question was focused on that. So these are the two redundancy protocols which have been adopted by IEC 61850. The example that I have shown is exactly a PRP architecture. This is mainly used and where we encounter all these interesting findings with a failover behavior, and yeah, this is what we are working on, and what also 9.3 likes to serve. And this is what we want to make work, and we are getting better with that. I'm not aware of anything that could come after that. Did that somehow answer your question, or did I
It,
miss a
it,
point?
it, it did. It did. I wanted to understand where the redundancy path is going, what standard it's following, and maybe if you can answer, is a specific use being defined in an updated 9-3 profile or other work area, or is it, yeah,
No,
the
no.
combination of the two is challenging, as you point out.
9-3 is focusing on the behavior of clocks and of boundary clocks, uh, and not so much on the behavior of the end devices, where we actually have some work to do. Uh, and I, I think 9-3 isn't, I'm sure it isn't contributed to the redundancy topic as such. Yeah, how this is then conveyed in a redundant network like PRP is a topic out of 9.3, and it's a topic on its own, because when you look at the chapter in the PRP standard about the mapping of PTP to PRP, it's more or less a disclaimer. It's saying we don't do all this duplicate handling that is present for the other traffic for PTP. Once you have understood that, you're a step further.
Thank you.
Another question? Any other question? Actually, I have a question, Fred. How about, I mean, like we have all of these like the standards and everything for power system, this in like mainly in distribution. How about, let's say, inside a data center where we have our own pretty much like, distribution grid and everything and so on? Like I get this question often, like because right now, again, we're using precision time for our servers and so on. Would we gain anything like from, let's say, I don't know, bringing synchronization to our PSU systems, where like any insight on that?
I'm sorry. The My point of contact to the electrical power industry is the power station and the substation, and those devices that I have shown you. That these companies maybe also have data centers might be true, but this is not the place where I can go. This is a different department. This is IT,
Yeah.
and we are OT.
Yeah. No, I mean, just from a technical perspective, like let's say, would you gain anything from like phasor synchronous like techniques, measurements of phasor? Do you have like anything like, let's say, standing waves or something like that? Is there things like this you think you can imagine? Because I think, as far as I know, like we run in AC inside the data center, but then at the rack level we go to, like with the PSUs, we turn to DC. So at that point, do you think anything will benefit from that?
Yeah, the synchronized phasor measurements are something uh, which help you very much to assess the status of the network. So stability assessment or something like that is wonderfully fostered by this synchronized measurements. But what you need to have to make this useful use of that is a system with relevant phase shifts and also some kind of elasticity in between. So otherwise, you have a tightly coupled stiff system, and there is not much to consider in terms of stability. So I would guess that inside the data center, you would not have such problems. If you had, I would very much look at your power distribution architecture.
Mhm. So yeah, like I mean, top of my mind, I was thinking that if I do like phasor measurements, like again across all the machines, I can have, let's say, certain capacitor banks or something that can kick in to do, I don't know, phase correction. That's what I was like thinking. I don't know, like
Yes, of course, this is imaginable when you have such a kind of control center
yeah.
uh, where you bring this information together and where you make some conclusions. This is, by the way, the big thing with the synchrophaser stuff. You can find a zillion of presentations where they have installed thousands of this and can store terabytes of that, and they have megabits per second here and there. But this is not something, let's say, very impressive because you only need a budget for that, nothing else. Uh, what's really interesting is what you do with this and how you make an assessment about the state of the system from this synchrophaser data. And this is a really super interesting topic. And there are own conferences looking into this. I think it's also a field where artificial intelligence could come to a useful application.
Mhm. Any more questions? Okay, so another question I had from you, remember in ITSF, I was asking you, like, let's say we go fast forward in 50 years, would we still have, let's say, in our case, 60 hertz, in your case, 50 hertz, just, there for satisfying the d phi over dt to make transformers work, or we can have it stable that we can actually use it as a source, as a clock source. Because like I have, to be honest, I have like this old clock that uses the 60 hertz, and it's pretty drifty. So it shows like the 60 hertz is really nothing.
So
It's
it
background.
shouldn't drift because in the States and in Europe, there is an authority who actually counts the cycles. And if the clocks fall back, the set point for the frequency is increased and vice versa to adjust these clocks. So there is somebody looking that even if you have under frequency or over frequency for a certain period of time, that on average you really have 50 or 60 hertz and that these clocks are accurate.
Oh,
What is not imaginable that is that you pin down the power system frequency at any instant to the nominal value,
I see.
because
Yes.
you need to have this slope, this characteristic, which is some microhertz per megawatt or whatever, because you never have a perfect balance between production and consumption. And to allow the system to work in between, where you bring in generation or remove generation according to the demand, you need to have this curve where the frequency is allowed to move a little bit.
I see. Okay. So is there like an ADEV graph for it or something, like an Allen variance to show like basically when it plateaus, when it goes up or something like that?
I really don't know if this is there, but as I said, it is counted. And I know in Europe, if the time deviation comes to a certain amount of seconds, then the set point for the nominal frequency is increased or decreased by 10 millihertz.
Interesting.
And then the whole
Correct.
synchronous system goes in this regard.
So Ernani has a question. Ernani, you want to? Ernani, if you're still there, make sure you're unmuted. I can ask the question Ernani was saying. Like, is asking about PTP under PRP. Very complicated issue, has not been completely solved yet. So
Yeah, I can agree to that. I think I made some statements in this regard. First of all, this redundancy mechanism that apply for the normal traffic in the PNP network does not apply to the PTP network or to the PTP traffic. And then the more clocks you bring in, and also redundantly connected clocks are then there 2 times, the more complicated your failover scenarios become. And it's actually a point that the IEDs, the devices which should synchronize themselves, they need to be able to handle that. But if you have 4 clocks in the system, you might run out of parameters to deal with that.
yeah.
And I said best practice is still evolving. There are some pilot projects or examples where they can cope with that, where they have learned how to do that. So at the ITSF, there was also this guy from Iceland talking, Birkir, and I know they are rolling out this stuff now on business as usual scale, and they have mastered this. But the point is not to make it too complicated.
Yeah. Okay. Any more questions? If none, this will be basically the last presentation for the year. And we wish you great holidays on behalf of OCP TAP, and see you in 2023. Okay. Bye, everyone.
Bye-bye.
Bye.